Alright, thanks for watching. And today I would like to give you yet another example of separation of variables, but this time with the wave equation and with what are called Neumann boundary conditions, where instead of specifying u at the endpoints, we specify the derivatives at the endpoints. And the cool thing is, this will lead to a new kind of series, so not the sine series, but the cosine series. So, again, if you want, the setup is, suppose we have a wave on a string from 0 to pi, and we say that we require the derivatives, the velocities at the endpoints to be 0, and initially the string, the wave, is like x squared, and with velocity cosine of 3x. And the question is, how will the wave behave? It rhymes for every x and t. And again, luckily the steps are the same as usual. So step 1, we separate variables. So suppose uxt, it's a function of x times a function of t. Then plug that into the wave equation. So utt equals c squared uxx. That means x times t, tt, equals c squared x times t, xx. But what's nice is, x is a constant here with respect to t, so it comes out. And the derivative of t with respect to t is just t prime. So here t prime prime. So what you end up getting is xt prime prime equals c squared x prime t. And then all you have to do is to rearrange this equation until all the t's on one side and all the x's are on the other side. So let's do that. For instance, let's divide this equation by x and put the other terms there. So what you end up getting after all this mess is x double prime over x equals t double prime over c squared t. Why did I do this? Because you want your x equation to be as simple as possible. Now, here's the cool thing. This side only depends on little x. Right? So it does not depend on t at all. On the other hand, we're saying that this function of x actually has to be a function of t. Because the right-hand side only depends on t. And here's the important thing. So in other words, this side, so this quantity, whatever it is, it's independent of x. Sorry, it's independent of t because there's just x. But I'm also saying the same quantity is independent on t. Let me do this again. This quantity is independent on t because it just depends on x. But it's also independent of x because it depends only on t. So basically it's independent of both x and t, and therefore it's just equal to a constant, which I like to call lambda. Other people like to call minus lambda. It doesn't matter. It gives you the same expression in the end. So we have that. Or if you're not convinced, call this quantity f of x comma t. We find that the t derivative is 0 and also the x derivative is 0. So f, whatever that quantity is, it's constant. And from this we get two different equations. On the one hand, x double prime over x equals lambda. So x double prime equals lambda x. On the other hand, t double prime over c squared t is also lambda. So t double prime equals c squared lambda t. Now, I know it's tempting to use t, especially for the heat equation, but for those kind of equations, it's very important to use x. Because it turns out now we can use the boundary conditions. And the boundary conditions will be very nice with x. They will be very ugly with t. So step 2 is to use the x equation. So we already know that x double prime equals lambda x. Now, let's use the boundary conditions. So we know ux 0t equals 0. But look, what is ux? So if u equals xt, ux is the derivative of this with respect to x, and that becomes x prime of x, t of t. In particular, ux 0t, you plug in little x equals 0. So ux 0t, that becomes x prime of 0, t of t, and that is 0. Now, here's the thing. This holds for every t. So unless t is 0 everywhere, you just get x prime of 0 equals 0. Now, it could happen, of course, that t is 0 everywhere. But in that case, u, which is x times t, just becomes the 0 function. And here's something important. We're looking for non-zero solutions of this equation. Because, first of all, the 0 solution isn't very interesting, but also it doesn't satisfy our initial condition. So we would like to find a non-zero solution of this. Therefore, we can actually legitimately conclude that x prime of 0 equals 0. And similarly for the other one. So on the other hand, from this, you can do the work and you conclude x prime of pi equals 0. So similarly, x prime of pi equals 0. That is good because now you end up with this boundary value ODE. You get x double prime equals lambda x prime of 0 equals 0, and x prime of pi equals 0. Good. And now let's solve this. So the next step, is what I like to call 3 cases, because depending on the value of lambda, you get different solutions. If lambda is 4, for instance, you get exponential solutions. But if lambda, let's say it's -1, you get sines and cosines. So we actually need to argue in terms of the value of lambda. So 3 cases. Case 1. Suppose lambda is positive. Now, you could have just do it with lambda. You get ugly square roots. But let's simplify our task a little bit. Because it's positive, we know it's the square of something. Then lambda equals omega squared for omega positive. Let me give you an example. If lambda is 4, well, you can write this as 2 squared. So lambda would be 4, omega would be 2 squared. And you can do this for whichever thing you like. Then solve our equation. X double prime equals lambda x. That implies x double prime equals omega squared x, which gives you the auxiliary equation, r squared equals omega squared. So r equals plus or minus omega, which gives you, in this case, exponential solutions. So x of x equals a e to the omega x plus b e to the minus omega x. Now use the boundary conditions. Use x prime of 0 equals 0 and x prime of pi equals 0. So x prime of 0, it's a omega e to the omega x minus b omega e to the minus omega x. You plug it in. That's x prime of x. Now you plug it in at 0. X prime of 0, it's a omega e to the 0 minus b omega e to the minus 0. And that becomes a omega minus b omega which you can simplify. So that becomes a minus b omega. And you know this is 0. And remember, omega is positive. So we can cancel this out. And we get a equals b. And I forgot to say, we know this is 0 because x prime of 0 equals 0. So in other words, x of x equals a e to the omega x plus a e to the minus omega x. Because a equals b, and we also have x prime of x. It's a omega e to the omega x minus a omega e to the minus omega x. And now we need to use the other condition. So x prime of pi, it's a omega e to the omega pi minus a omega e to the minus omega pi. And again, if you want, that's a omega e to the omega pi minus e to the minus omega pi. And we know this is 0 because x prime of pi equals 0. Now, remember we can cancel out omega because it's positive. And here's the thing. We could cancel out a. The only problem is, what if it's 0? But look, if a is 0, then the whole solution is 0. And we don't really want the 0 solution. So it's actually okay to assume that a is non-zero and cancel this out. Then what we get is this expression is 0. So in other words, e to the omega pi equals e to the minus omega pi. Take ln's, omega pi equals minus omega pi. It's my favorite kind of pi. You can cancel it on pi, and then basically you get 2 omega equals 0, and then omega equals 0. But that's a problem, because then lambda is omega squared, and that's 0 squared, and that's 0. And it's a contradiction with the fact that lambda is positive. Lambda is positive, and in particular what we can conclude, in the case lambda positive, there are no solutions. Okay, not a problem, because we still have 2 other cases. So case 2, I know it's a long process, but remember you do find a solution of the wave equation, which is pretty cool. And by the way, in case you're wondering, no, D'Alembert's formula does not work here, because D'Alembert's formula is just for the whole line. Here we just have a finite interval. Okay, so lambda equals 0, then our equation becomes x double prime equals 0x. So x double prime equals 0. So x, in some sense, is just a linear function. So ax plus b. And then you just need to calculate x prime. So x prime of x just becomes a. And in particular, x prime of 0, that becomes still a. But we know by our boundary condition that x prime of 0 equals 0. So we know a equals 0, which tells you x of x equals b. And remember this, just for a second. Now, let's see what we have for x prime of pi. Well, x prime of x is a, which is 0. And the point is, if you have this solution, differentiate it, and let x equals pi, you actually also get 0 automatically. So the question is this a contradiction? Well, actually no, because this is indeed a solution of your equation. So be careful, don't just automatically dismiss that case, because for the other cases it didn't work, but here it actually works. Third case, lambda negative. Then similarly, we can write lambda is minus omega squared. things like minus 4, it's minus 2 squared for omega positive. Then x double prime equals lambda x implies x double prime equals minus omega squared x. With auxiliary equation, r squared equals minus omega squared. So r, it's plus or minus omega I. Which gives you the solutions. X of x equals a cosine of omega x plus b sine of omega x. And which is good, which is kind of the solution that we want, because waves aren't really exponential, they're like cosine-y, and now we just need to calculate the derivative and plug it at 0 and pi. So x prime of 0, so x prime of x, first of all, it's minus a omega sine of omega x plus b omega cosine of omega x. Well, x prime of 0, it's minus a omega sine of 0 plus b omega cosine of 0, which just simplifies to b omega. And we know x prime of 0 is 0. So therefore, we can just say, we cancel out the omega because it's positive, and you end up getting b equals 0. Which tells us from here, b is 0, so x is a cosine of omega x. And we'll need this in a second. Good. And now we just have one more condition. So if x is a cosine x prime of x, it's minus a omega sine of omega x. So x prime of pi, it's minus a omega sine of omega pi. And we know this is 0. And just as before, we can cancel out omega because it's positive. This term, unless it's 0, we're okay, we can cancel it out. But if a is 0, then our solution is 0. So just assume it's non-zero. So we get x prime of pi, it's sine of omega pi, and that's 0. I know it's crazy, right? Because you're like, oh no, we might just get a contradiction again. But the question is, who saves the day? Well, Peyam saves the day. Oh no, okay. Don't tell the department, but, oh no, okay. I do still save the day because omega pi is Peyam. The zeros of signs are Peyam, and then you actually get omega is m. And that's from 1 to infinity. So what is our conclusion in this case? This means that lambda, it's minus m squared. Yeah, lambda is minus omega squared, which becomes minus m squared. And our corresponding solutions are those ones, cosine of omega x. So if you want x of x, it's cosine of omega x, so cosine of mx in this case. If you did it on the interval 0 to 1, you would find cosine of pi mx. So it doesn't matter. Therefore, what is our grand conclusion? Because don't forget that case 2 also worked. So we do have 2 things that worked. So how can we have another one here? So we did have case 2 that worked, and now case 3 that worked. So just a little conclusion. Remember, we did have lambda equals 0, which gave us x of x equals b. Yeah, sure. Let's call it b. And then we also had lambda is minus m squared, which gave us x of x equals cosine mx. Now, any multiple of this. The nice thing is, though, in theory, you could just combine those two cases. Because if m is 0, then lambda is 0, and cosine mx is 1, which is just, and b is just a multiple of 1. So you could do that. I did it in lecture. It worked horribly because the t equation screws it up. You'll see why. So now, next step, I believe that's step 4. Now let's look at the t equation, which I believe was something like t double prime equals lambda c squared t, which becomes slightly different, or maybe was it minus, check, no, it's good, this one's good. Now, based on the value of lambda, we get two different equations. So for lambda equals 0, this gives you t double prime equals 0. So t, it's at plus b. So in this case, we have a linear function. But for all the other cases, lambda equals minus m squared. You get t double prime equals minus m squared c squared t. With auxiliary equation, r squared, it's minus m squared c squared. So r is plus or minus mci. It's the long-lost brother of MC hammer. So mci, and you can't touch this, just like the eraser that just fell. And which gives you the solution, in this case, cosines and sines, but with respect to time. So t of t equals a cosine of mct plus b sine of mct. That's good. So you have solutions, right? And I like to remind you, for lambda equals 0, x of x was just some constant. For lambda negative, x of x was cosine mx. So all you need to do is just take linear combos of those. So that's step 5. You think we're done. We're like sadly nowhere near done, because we still, well, we found a general solution, but we still need to plug in the initial conditions. So I think that was step 4. Step 5. Just take linear combos. Because you see, the point is, we found basically a basis of solutions, so specific solutions of the equations, but because the wave equation is linear, the magic fact is, if you take linear combos of solutions, you still get a solution. So, in other words, if you take linear combos, first starting with the case lambda equals 0, so if you take u is xt, because all of those are arbitrary, you basically get at plus b with possibly different constants. So uxt is, in this case, at plus b. That was case 2. And you can take linear combos of all the other ones. That's for m from 1 to infinity. So you multiply this by this and take sums. And what you get is essentially the sum from 1 to infinity of all this stuff. So a cosine of mct plus b sine of mct times cosine of mx. And to emphasize that the constants depend on m, we put little m's here. am cosine of mct plus bm sine of mct. Whew. Okay, that's good. So again, that was case 3. And now, I know I'm getting tired too. We need to plug in the initial conditions. So I like to remind you, u of x0 was x squared. Okay, maybe, yeah. So all we need to do, plug in t equals 0. So ux0 equals a0 plus b, and then plus sum from m from 1 to infinity, am cosine 0 plus bm sine of 0 times cosine mx. And what this becomes is b plus the sum from 1 to infinity of am cosine mx. And which, if you want, just becomes a cosine series. So you can actually rewrite this as a sum from 0 to infinity of am cosine of mx, where if you want a0 corresponds to cosine 0x, which is just b. So, and remember, what do you want this to be equal to? You want this to be equal to x squared. Now, as I said, at least in lecture, before like the 1850s, this was a completely unsolved problem. The question is, how can you write a function in terms of cosines? But luckily, at some point, Joseph Fourier came along and invented Fourier series, which means we can actually solve this now. How do you do this? It's basically orthogonality. So first, take care of the case a0. And again, I hate this convention where people use a0 over 2. My philosophy is just do it directly. So a0, what do you get? Again, which I like to remind you, it's b. We just hug, if you want, the function x squared with the function what? You integrate that from 0 to pi, in this case, dx, over the integral from 0 to pi of 1 times 1 dx. It's like the orthogonality formula, right? X dotted with u over u dotted with u. It's the same thing. And so integral of x squared from 0 to pi, it's pi cubed over 3. And integral of 1 from 0 to pi is just pi, and therefore you get pi squared over 3. That's your first thing. And again, no silly thing of dividing by 2. But for the other one, slightly different. So am now becomes integral from 0 to pi of x squared cosine of mx dx divided by, if you want, the integral of cosine squared mx, but that integral, essentially what it becomes, you just repeat this number here, pi, and you multiply it by 2, because you're talking about the half interval from 0 to pi. And how do you do this? It's with the famous DI method by Black Pen Red Pen. So you take x squared and cosine mx. You differentiate the hell out of this. So 2x, 2 and 0. Put pluses and minuses. And here you anti-differentiate. Sine of mx over m. And then minus cosine mx over m squared, and then minus sine of mx over m cubed. And then you take the cross terms. And what you get is just 2 over pi times, let's see, x squared sine of mx over m, and then plus 2x cosine of mx over m squared, and then minus 2 sine of mx over m cubed from 0 to pi. Probably brought to you by American Express, MX, right? So, no, That was not sponsored by it. But here's the cool thing. So it's horrible antiderivative if you want, but notice sine of Peyam is 0, and sine of 0 is 0. So basically all those terms drop out. If you do that, moreover, at x equals 0, this also drops out. So the only thing that's left is the pi term. So this becomes 2 over pi, 2 pi, cosine of me, pi m, over m squared. And then the pi's drop out, and we get 4 to the minus 1 over m squared. And this is our AMs. So that's good. Let me just write this down in case I forget. So B, it's pi squared over 3. And then AM, it's 4 times minus 1 to the m over m squared. And you think we're done? We're not quite done. We still have the UT term. So that is good at least that we found one of the two. Now, almost last step. I like to remind you UT xt equals, this time I believe, cosine of 3x. But here's the nice thing. We have our uxt here. And so really all we need to do is to differentiate this. So let's calculate the derivative of this with respect to t. That becomes a plus sum from m equals 1 to infinity of, I believe, minus am mc sine of mct plus bm mc cosine of mct cosine of mx. And then you just need to plug in t equals 0, utx0, that becomes a plus sum from m from 1 to infinity. But you see, if you plug in t equals 0 here, this term disappears. And this term is just 1. So it's just the sum of bm mc cosine mx. This just becomes 1. And what you can do, you can just write it as one sum. So it's the sum from m equals 0 to infinity of bm squiggle cosine mx. And we know in this case it equals to cosine 3x. Where at bm squiggle, so b0 squiggle is just a, and bm squiggle is just mcbm for m equals 1 to infinity. Now, usually you need to solve for a Fourier series, but here's actually quite nice. Because what is this saying? It's saying that b0 squiggle cosine 0 plus b1 squiggle cosine 1x plus b2 squiggle cosine 2x plus b3 squiggle cosine 3x, etc., equals to cosine 3x, which is 0 cosine 0x plus 0 cosine of x plus 0 cosine of 2x plus 1 cosine 3x plus that. So in other terms, you don't need to use Fourier series. You just need to use really linear independence to conclude that actually you can just compare the terms, term by term, and essentially what you get is everything is 0 except for b3 squiggle. 0, therefore m not equal 3, and then bm, b3 squiggle equals 1. And remember, b3 squiggle becomes 3c b3 equals 1. and basically get B3 equals 1 over 3C. Remember, there we go, BM squiggled is MCBM. So B3 squiggled is 3C B3. And that's good. So, and again, all the other terms are 0. So we essentially get A equals 0. And then Bm equals 0. And therefore, finally, we have our solution. So I believe was at step 7. Yeah, now we have step 8. General solution. So uxt, I like to remind you, it's, I think, at plus b plus the sum from 1 to infinity of, I believe, am cosine of mct plus bm sine of mct times cosine of mx with what values? So let's see. So A was 0. B, I wrote this down, was pi squared over 3. Now, AM was 4 times minus 1 to the m over m squared. And then, well, Bm was 0, except for B3, which is 1 over 3c. So, if you want, you can write this down more explicitly. As follows, so that becomes, so A is 0, so pi squared over 3, plus sum from m from 1 to infinity of, so am, it's 4 times minus 1 to the m over m squared cosine mct plus basically 0, that's what I want to emphasize, 0 times sine of mct times cosine of mx. And again, this 0 everywhere except at 3, which is 1 over 3c. So this is how we can kind of think about this. And notice what is nice. So in terms of our interpretation, it says that the waves, what it looks like, it's sort of like pi squared over 3, but it oscillates, you know, in terms of space, it goes like cosine of mx, but it oscillates with time like cosine mct, with like smaller and smaller contributions of our wave. So it might look initially maybe like x squared, but then over time it just goes like x squared, but like up and down. That's what this a cosine of mct kind of looks like. And congratulations, I know that was a long problem, but it really illustrates all the steps in separation of variables. So if you're still watching, congratulations. And if you want to see more math and more PDEs, please make sure to subscribe to my channel. Thank you very much.